Alright, so there are three types of intermolecular forces. So if we look at the word intermolecular, molecular, between molecules. So when we look at this, we're talking about it in terms of molecule to molecule. This only applies to covalent molecules. It does not apply to ionic molecules. So the first is going to be London dispersion. Every compound has London dispersion. This is the weakest. Every compound, with the exception of ionic compounds, has London dispersion. Now we're going to change this, and we're just for consistency's sake, and say that molar mass determines the strength. Dipole-dipole is the next strongest. This applies to compounds that are polar. So if my shape is polar, then my molecule is polar, meaning I have a dipole-dipole force. Again, this increases as the molar mass increases. The third is hydrogen bonding. This is the strongest type of dipole, or the strongest type of intermolecular force, and it only applies to HF bonds, HN bonds, and HO bonds. FON. F-O-N. Okay. Anything else bonded to hydrogen is not a hydrogen bond. It has to be fluorine, nitrogen, or oxygen. This is the strongest of all the IMFs, and it increases as the molar mass increases. Using IMF to determine comparative boiling points and water solubility. Would it take more energy to boil a compound where there are stronger forces holding one molecule together or weak forces holding one molecule together? Obviously, this is going to be strong. More energy to break strong bonds. So compounds in order of highest boiling point to lowest. H bonds, dipole, LD. Now ionic is going to be even above hydrogen bonds. So ionic, again, is going to be the strongest, and it increases as molar mass increases. So heavier compounds are going to be stronger than lighter compounds. Alright, so if we do our little chart here, I'm going to go ahead and do the bond polarities first. So I'm just going to do these quickly. And I'm actually just going to do the first four of these. I'm not going to do the whole chart. So NH3, nitrogen has 3, hydrogen has 2.1, so that's a 0.9 bond polarity. 3.5 minus 2.1 is 1.4, I think. Yeah, 1.4. 4 minus 2.5 is 1.5. And then magnesium and chlorine. 3 minus 1.2 is 1.8. Okay. Now I'm going to do my dot structure. Nitrogen is in group 5. It has 5 valence electrons. That's a total of 8 valence electrons. 6, 7, 8 valence electrons. 32 valence electrons. And then magnesium chloride, this is different because this is ionic. Because this is ionic, it's got the different bond polar, or the different dot structure. It's going to be Mg2 plus Cl7 yields Mg plus Cl plus 2 minus 1. So let's go through and do the dot structures for my 3 covalent compounds. N is my central atom. H's go around. Remember that a line represents 2 electrons. 2, 4, 6. Make the central atom happy. 8. Water. Oxygen's the central atom. Make oxygen happy first. 2, 4, 6, 8. CF4. C is the central atom. F's around. 2, 4, 6, 8. 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. Alright? Molecular polarity. We determine this by if the central atom has a lone pair. If the central atom has a lone pair, I'm polar. So I'm polar, I'm polar, I'm nonpolar. It doesn't apply to ionics. So for IMFs present, remember that LD is present everywhere. except for ionics. And then dipole is present in any of my polar compounds. And hydrogen is present in everything bonded, or nitrogen bonded to fluorine, oxygen, or nitrogen. So H bond, H bond. Now, to do my comparative boiling point, I'm going to list these from 1 to 4. 1 being the highest, 4 being the lowest. And this is pretty easy because I only have one ionic compound, so this has got to be the first one. Now, the second one is either going to be NH3 or H2O. And I'm going to determine which one it is based on the boiling, or based on the molar mass. So water has a molar mass of 18, NH3 has a molar mass of 17, meaning that number 2 would be water, number 3 would be NH4, number 4 is going to be my nonpolar compound. You have to be able to rank these based on their comparative boiling point, from highest to lowest or from lowest to highest. It's based on molecular polarity and molar masses. All right, and the last piece to bonding is going to be alloys. So the metallic bonding theory says that metals form bonds, but they're not true bonds. They're more of interparticle attraction. So basically what happens is I have a mix of metallic atoms that delocalize. So the electrons become detached to the detached, no, that's not the right word. They basically separate out from the nucleus. So once they've separated out, they create this sea of electrons, so this sea of negativity, that allows for a lot of the properties of metals to be true. It's why metals are malleable. Malleable means able to be pounded into sheets. It's why metals are ductile, which means pulled into wire. It's why they conduct electricity, because the electrons are constantly moving. So this is why metallic compounds have the characteristics that they have. And an alloy is going to be a mix of two or more metals. So an alloy is a mixture. It could be homogeneous, could be heterogeneous, of two or more metallic compounds, two or more metal atoms. So some common ones are cast iron. Cast iron is a mixture of carbon or iron. Bronze is a mixture of copper and tin. Gold is probably the most important alloy, and when you go to buy jewelry, what you're buying is a gold alloy. So it's pure gold mixed with silver or copper, and this allows it to increase its strength. So that's really the reason we have alloys, is because they're stronger and more durable. So 10 karat gold is going to be your most durable gold. 24 karat gold is going to be your least durable gold, because it's the highest percent of pure gold. Pure gold is pretty soft. It's able to be scratched or destroyed fairly easily. So that's why we mix it with elements like silver and copper that are a little bit stronger, that can withstand a little more abuse.